Yes. Just set it up, yeah. That's what it says. Read the instructions.
So it took me so long. I was just trying to solve every one. I was like, why do you have 20 minutes?
Yeah, no. No, just put it together, yeah. Okay, everybody turned it in? All right, so the solutions to this, the region in question here is this one. And so you're going to have to figure out where the two curves intersect. And so here are the two curves. So you have to figure out where they're equal to each other. And then move everything to one side. It's a quadratic. You can factor out a GCF, and then the remaining three terms factor, and then you get 5 and 2. So you got your 2 points of intersection. And then you just find the area. So the area will be this rectangle, which would be your top function minus your bottom function. Top function here being the negative x squared plus 10x minus 13, the bottom function being the dotted one. So you just put integral 2 to 5, top function minus bottom function dx, you're done. That's the first one. Now, you want to take the volume of the solid generated by taking that region, going about the x-axis, means you want to wrap this around the x-axis, which is going to be a washer method. So the only thing that changes is that you have to throw a pi out here, and then it's the top function squared minus the bottom function squared dx, and you're done. Then you want to rotate it around the line y equals -3. That means, imagine that there's a line down here, -3. Straight line would be preferred. And you want to wrap this around that line instead of the x-axis. So what you have to do is figure out what this total distance is, which would be 3, which comes from here, right, that distance, plus the distance from the x-axis up to the top function, which would be 3 plus this right here. So where do I have that? 3 plus the top function, then all of that quantity squared. Then to get the bottom radius, which is from here to here, you do the 3 and then plus the bottom function. So it's the same thing, 3 plus the bottom function, then all of that quantity squared. No, the dotted one is 2x squared. Solid one is this one. That's why I did dotted and not solid, so you could tell the difference. Okay, then you want to rotate around the line y equals 14, which is above these functions up here. And that means, let me draw a different rectangle. You have to figure out what the distance from the axis of rotation is to the outer edge of the rectangle. So you know that the distance from the axis of rotation all the way down to the x-axis is 14. You subtract from that this amount right here, which is the dotted function. 14, take away the dotted function, all of that quantity squared. Then the inner radius, or the inner distance, which would be the axis of rotation to this edge, which again would be the 14, take away that negative x squared plus 10x minus 13. So this one. And then the last one is to wrap it around the y-axis using shells. So we're going to take this rectangle, go around the y-axis this way. So for that, all you need to know is really the radius, the distance from the axis of rotation to the rectangle, which is actually just the x-coordinate of that rectangle. So the formula was 2 pi times the radius, which is x, and then the top function minus the bottom function. That's it. Okay, so that's what I was looking for. Really, the reason I want to give a quiz is to give you an idea of, you know, this is a type of problem you would see on the test, but you would have multiple problems like this. So it becomes a time issue. You know, you don't want to take 45 minutes on something like this if you're going to have this along with everything else, right? Our test is, what, a week from today. So, all right, but we still have a lot to do. So let's get to today's material. We finished off last class. I had just started to introduce you to this concept of shells. The main difference between washers and shells is that your axis of rotation runs parallel to the rectangle within your region, as opposed to washers where they're perpendicular. And it gives us a way to get around issues like this where we'd want to go around the y-axis, but we could not do a rectangle horizontally because your top and bottom function or left and right functions are the same thing. Was there a question? No. So what I'd like to do is I'd like to do this problem again, but I'd like to change our axis of rotation from the y-axis to something else. All right, so that's where we'll start. So it'll be linear. Okay, so I'd like to take this curve. I'd like to rotate it about where the heck did it go? There it is. So it went out to 3. So let's start with about the line x equals -3. So x equals -3 is a vertical line, right? Last class we had already drawn this out. It was at 2, and our little parabola looked like this. Came up like that. And it hit that line y equals 1 there. So we had, this was our region. So this time we want to rotate this around the line x equals -3, which would be over here. We want to rotate it this way around this. So I'm going to go again to vertical rectangles because that's really my only choice. I can't draw it horizontally, right? Not easily. I want to wrap that thing around this way, which will create something that looks like this. All right, so something like that. It's not a washer, we call that a shell. It really is a cylinder, it just has a very narrow wall. All right, and so what we do is we add up all of them. Yes? Your rectangle is either perpendicular or parallel to the axis of rotation. So if this line that you're rotating around is parallel to the rectangle that you're drawing, then you're going to have to use shells. See, look, what if I try to do it the other way? This red part here and this red part here come from the same curve. So you couldn't do it that way. Well, I mean, you could. You'd have to break it up into, like, it would turn out to be like a square root, and you'd have to look, one of them's the positive case, one of them's the negative, and to get around that, we just go with vertical. Yeah? Your picture will still have the same issue. You mean make all your, like make this x, make that y, make this x, make that y? No? Yes, but if that's what I'm saying, look, if you solve for x here, you're going to eventually have to take a square root, which means you're going to have plus or minus, which means you're going to have two different functions. Right? You have a positive case and a negative case. Right? What would be the first step to solve this for x? Square root on left, square root on right. When you do square root over here, you have to do plus or minus. And then you'd move that 2 over. So you'd have x equals 2 plus root y, and the other one would be 2 minus root y. And yes, you could then look at this as being two different functions. But I'm saying you have to go through that, and not every, you can only do that because it's a parabola. If it was something else that you can't do that easily with, you'd be kind of stuck. This method is very efficient for handling something like this. I hope that makes sense. Okay, so on your formula sheet, or the handout that I gave you, it was the formula for shells was 2 pi integral a to b. Then on the thing it said like u radius or something. And then what did it say here? Top, something like that. Top, F out, F in. But I said in class this should be basically your top minus your bottom. And this will be with respect to x, yes. That's pretty much what we're going to do. So what is the top function in this case? So I'm looking at my rectangle. What's the top function for this rectangle? Y equals 1, right? Y equals 1 is my top function. What's the bottom function? Well, that's the parabola, right? So x minus 2 squared. That's what will go in here. My radius, though, is the part that gets a little tricky. It's the actual distance from the axis of rotation to my rectangle. And my rectangle, to move out here, I picked some arbitrary point, right? Between, what was it, 1 and 3? Is where those hit each other? I have to pick an arbitrary point between 1 and 3. That arbitrary point is the x-coordinate of that rectangle. So that distance from here to here is x. But I have to tack onto it how much more? 3. So here's how my formula will translate. I have 2 pi integral, I'll go 1 to 3, we did that last class. And then my radius would be 3 plus x or x plus 3, it doesn't matter how you write it. But that needs to be in parentheses. And then inside top function, which was 1, minus bottom function, which was x minus 2 squared. All of that dx. Make sense? So in the formula for shells, we don't square anything, right? Like with washers, you had like the top squared minus bottom squared, and you had a pi outside. Or you did left squared or right squared minus left squared, or whatever we're looking at it. Here we don't, with the shells, there's no squaring. You have to compensate though for that radius. All right, so that would be the setup. Then you would go through and just like multiply this all out, figure it all out, power rule on each term, you'd be done. So ... Questions? All right, let's do the same problem. We'll just change our axis of rotation one more time. This time, let's move the axis of rotation to the other side of the region, to the right side of it. So how about x is 7 or something like that? So here's our picture. We had y is 1 here. We had our parabola, went up like this. We had our region. And then over here, 3, 4, 5, 6, 7's out here. We want to rotate around this. So if we were acting like this were a brand new problem, we would be thinking about how to draw our rectangles. And hopefully, again, you would look at that and say, hey, vertical rectangle is going to work real nice, right? So you draw your vertical rectangle, some arbitrary rectangle in here. You know that the rectangle is vertical, that's parallel to your axis of rotation, so you want to use shells. And you just need to know top and bottom function, which we know, right? 1 and then the x minus 2 squared. All we have to determine is the radius. So our radius goes from the rectangle to the axis of rotation. that distance. Keeping in mind that the distance from the y-axis to the rectangle is what? X. And the distance total from the y-axis all the way here is 7. So this would be 7 take away x, right? 7 take away x. So 7 minus x is our radius. So set it up. The volume would be 2 pi, integral 1 to 3 again, 7 minus x, and then your top function minus your bottom function, squared. It was not squared, but the function was squared itself, x minus 2 squared, and then dx. We're done. Now, there are problems that you could extend this now. Well, are there any questions on this? Yes? 2 pi came from the fact that when we have this shape and we were trying to figure out what its volume was, we cut it and we laid it open. And when you do that to find its length, it involves the circumference of the circle, which is 2 pi r. So in the formula, it's 2 pi radius. And the radius is this part. Where when we did the washer method, you were trying to use the formula for a cylinder, which was pi r squared. So there's no 2 pi, it's pi. All right, so shells, everything I've done with shells so far, we've rotated around the y-axis, or we've done like vertical lines. But you can imagine that this could be extended also to go around the x-axis, right? So if you were given a problem, something like this, let's just change it up so you can see what I mean. If I say x equals y minus 2 squared and x equals 1, that's our region. And we want to rotate it around the x-axis. I'll do that afterward. I just wanted you to see that you could use the same concept, all right? So first you start out, you graph this thing. This is going to be a sideways opening parabola. So it would look like this. Up here at 2, y equals 2. It would open up like that. Then you have x equals 1, which would be this. And so you have this region. And we want to rotate that around the y-axis. I mean, x-axis, thank you. Right? So do you see that you see that your vertical rectangles won't work here? Not easily again, right? What would be easier for us to do would be for us to just do a rectangle sideways, because I know that this green line vertically here is x equals 1. I know that this, which we were calling the right function, right? The left function here would be this x equals y minus 2 squared. But now by forcing my rectangle to be horizontal, my axis of rotation is also horizontal, and so I'm forced to use shelves. So my formula should be what here? 2 pi integral. What we're gonna be looking at our y values, right? It's like our C and D. It's still 1 and what? 3. So we're still going to go 1 to 3. But now the radius. So the radius here is the distance from your rectangle to the axis of rotation, which is no longer your x-coordinate. It is now your y-coordinate of your rectangle. So that's going to be y. And then instead of top minus bottom, it's going to be right minus left. So you have 1 minus y minus 2 squared d y. I mean, that's the exact same problem. Everything switched. All the x's and y switched. But I just want to show you that with shells and washers, you pretty much can handle any region wrapped around any vertical or horizontal axes, as long as the axis doesn't cross through the region or something like that. Okay? Any questions? You mean where like our region itself would be asymmetric? We won't do that in here, no. You mean like where your region is so crazy that it's neither like a function of x nor y? We won't do something like that in here. I guess you would talk maybe like a region like that would look like some like clover or something like that. We would do that in a different coordinate system. We would use a different coordinate system because it would be easier to define the function that way. You know what? When it comes to rotations of regions in a calculus sequence like this, even though Cal 1, 2, 3, and then some classes have 4 calculuses. By the way, if there's usually Cal 1 through 3 or it's 1 through 4, the only difference is if it's 1 through 3, there are 4-hour credits. If it's 1 through 4, there are 3-hour credits. So it's the same number of hours, just FYI. So getting back to your question, in a calculus sequence, when it comes to rotations of regions around things, we stick to what you've seen. We don't go asymmetrical. We don't try and rotate a region around a line that's not vertical or horizontal. We don't do that. Now, can it be done? Yes. But what happens is later on in higher math courses, it becomes sort of a trivial result of kind of a bigger system of things happening. You know, you just like rotate your, I mean, imagine if I rotate this whole thing over, or you know what, that's probably not a good picture. What if I had a region like this? And I want to rotate this. That would be easy to do around the x-axis, around the y-axis. It would be easy to do around horizontal and vertical lines. But how do we do it along that, around that red line? Well, we just take the whole picture and we just rotate it, right, to make our red line horizontal. And what happens is it changes our region. Our region is going to be maybe skewed a little bit like this. Okay, maybe it's going to look like that. That's no longer a function of x and y, but what you could do is you could come in here and like try and cut it up, you know, and deal with certain parts of it. So it requires translations in the plane, but it's beyond the scope of a normal calculus sequence. All right, you won't find that usually in any calculus book. Okay, so that's shells. The next thing we're going to do is, this topic is completely different than rotations. All right, so a lot of times when I get to this point, students are going to look at what I'm about to do now, and they still think we're rotating things, and we're not, okay? So keep that in mind as I show you the following animation. That's code. Ignore the code. All right, so here's what we're going to do. Okay, so let's say we have a parabola that opens up and a parabola that opens down, right? So if we take that and I tell you, look, for that region, I'm going to create from it, well, you know, let me draw it on a different page so you can see this. I can't draw on top of that. Okay, so there's my region, right? Forget that there's all these little cross-section things in there, all right? But I'm going to take an arbitrary rectangle in here. Let's see if I can draw on top of it. Yeah, there's a rectangle, all right? Maybe I can do this region. Oh, it won't let me highlight. Weird. Okay, so I'm going to take this arbitrary rectangle right here. And what I'm going to do is I'm going to lay that rectangle out on the ground, all right? See that rectangle laying on the ground? Like that, just laying down. Then from that rectangle, I'm going to create a square. So what I mean by that is go up with the same rectangle, go over with the same rectangle, and go down with the same rectangle. All right? See that? And what I've done is I've created this like box-looking thing. right? Now, I also don't want it to be hollow on the inside. I want it to be solid. So it really looks more like this. Okay? So I've created this square parallelepiped. And the important thing is that since I said it's a square, all the lengths are the same, right? All lengths are the same. And the size of the square is actually dictated by where my rectangle was in here, right? If I move this further to the right, if I would have chosen a rectangle, let's say here, can you all see that all right? Right, that rectangle, and I lay that one down, it's a little shorter than the last one was, right? And so the shape I would get would be more like this. Same shape, but not as big, right? In fact, if I moved all the way kind of right to the edge of this, I would have a tiny little square, wouldn't I? Do y'all see that? And the biggest square I would get would be right in the middle, wouldn't it? So what I would like to do is I'd like to create an object where, imagine a three-dimensional solid, where the bottom of the solid is this region, but the top of it, okay, the part above it are all these rectangles. Or, sorry, squares. What would it look like? So that's what this is. Okay, so let me turn this sideways in three-dimensional space so you can see it. Okay? So what I was trying to get you to see was, remember I said I had these little squares in here, or these little parallelepipeds? One of those is in here. Let's say the red one would be somewhere around, let's say here. Do you see it? Now, the width of that little parallelepiped, the width of it is dx, right? It's very, very infinitesimally small, the width. And then the black one would be further down, like somewhere around there. Does that come out okay? Yeah, y'all can kind of see that, right? So do you see that with all those squares, that's the weird kind of shape you get? Do y'all see that? It's kind of odd, isn't it? The question would be, what's the volume of that? Solid. Let me do same sort of principle. Let's use the same base. Okay, let's use the same base. But now, instead of forming squares above the base, let's do equilateral triangles. So let's go back to this. I'll do a new page. Let me take this guy. So it's the same thing. I'm going to take these cuts, this red one, this black one, but over here, when I lay them down, if I'm going to make a triangle, then it's equilateral triangle. It's going to look like this instead. Y'all see that? And then the black one would be the same sort of thing, just a little bit smaller, right? So as you moved out to the edge, these little triangles get smaller and smaller. They come down to a point. That's a different solid, right? It's a totally different solid. And so it should have a different volume. So here's what that one looks like. Can you all see the triangles in here? They go up to a point and then back down. Let's contrast that again with the squares. There's the square one. There's the triangle one. See the difference? Squares, triangles. What if instead of doing a square or a triangle, I use that little slice rectangle to create a semicircle? So above it, I do a half circle on top. Then it would look like that, wouldn't it? See the little circles in here? What if I did full circles? Okay, so if I did half circles, the diameter would be that rectangle, wouldn't it? The diameter all the way across would be the rectangle. So the radius would be half of that. The circle, full circle would mean don't just go halfway, go the whole way, right? Now you've got, it going below the x-axis, or below that plane also, right? It's got them on both sides, as opposed to this. It's not supposed to be hollow. That's just, I figured I didn't need to make it solid. And then let's see, rectangles. What's the difference between rectangles and squares? Well, with squares, I'm saying that this length is equal to this length, to this length, to this length. With rectangles, the proportions don't have to be the same. So I would have to specify how the rectangle is defined. Like I'd have to say, like the height is twice the width or something like that. I would have to tell you what it was. But do you all see that these objects are in no way the same as these regions revolved around x-axis, y-axis? Do you all see that? Okay, so what we're going to need to do in order to come up with a formula for these volumes, every problem is unique. Every single situation is unique. So we're going to need to be able to take one of those slices. We're going to need to look at it. We're going to have to come up with a formula for that volume. Once we find the formula, we integrate to add them all up. All right? So let's just go for it. So let's say the base of a solid is the intersection of y equals x squared minus 1 and y equals x squared, 1 minus x squared. So I'm telling you right now, the base of a solid is the intersection of these two parabolas, right? By the way, we are doing exactly this right here. We are doing this, that blue one and that red function are exactly x squared minus 1 and 1 minus x squared. That's what they are, all right? So the base of a solid is the intersection of those two. Find the volume of the solid if perpendicular cross sections are squares. We'll start with that one. We'll do circles. Hang tight. So we have to all understand what we mean by perpendicular cross sections. What we mean by this is if you were to take this picture right here, trying to get it like we're looking straight onto it, right? So we're looking from the top down onto this solid, right? The ground is the XY plane, yes? If we come in here and take a cross section is, you know, you got a turkey, you cut it, right? Something like that. We are going to take this and we're going to do a perpendicular cross section. What they mean is this cross section, the cut that we make, okay, the blade that we come through is perpendicular to the plane. So if the ground is like this, we are perpendicular with that blade, straight down through the solid, right? And that blade is not twisted this way or this way. It's parallel to, it would be parallel to the y-axis in this case, right? And perpendicular to the x-axis, right? So that needs to be understood as we proceed. So when the book says, or I say in a test, perpendicular cross sections, we're all doing the same thing, all right? So we're going to take perpendicular cross section, and when we take that cross section, I'm saying it's squares. So when I cut it, look at it from the side, it's a square. That's all that's given in the problem. All right, that's the whole problem stated out. So here's how we would go about this. We'd start with the graph. They hit at 1 and negative 1. You could find that by setting them equal to each other, right? So they hit at 1 and negative 1. That, whoa. That is the base of our solid right there. Perpendicular cross sections form squares. So now I'm going to come in here, I'm going to draw my infinitesimally narrow perpendicular slice cross section. That would be where the blade hits the ground, right? But it's got this infinitesimal width to it. When I bring that out over here and I lay that down on the ground, I now form that square. So go ahead, I'll do the square in like green or something. Come up, do a square. That's supposed to be a square. Okay? Terrible. Terrible square. You get the idea though, right? My question to you is, what's the volume of that parallel pipette, that little box? What's its volume? So you need length, width, and height, don't you? Okay. So what's the width of it? How wide? That's usually the easiest part. dx, right? How long is this from here to here? It's this top function, right? Minus the bottom function. Just like we did before, right? It's the top minus the bottom. So for us, the top function was which one? The red one up here? That was 1 minus x squared. The bottom function was x squared minus 1, right? So this would be what? 1 minus x squared, the top one, minus the bottom one. Do y'all see that? Which is really, if we clean that up, what? Two minus 2x squared. It was a good spring break, huh? Understood? That is the length of this side. Okay, well, what's the length of this side then? Same, because it's a square, right? That's what I said. It's a square. So the volume of this would be what? The volume of just this little sliver would be 2 minus 2x squared times itself, right? So squared times dx. That would be the volume of that one little sliver. And what do we need to do? Take all the slivers, right? And add them up. Now keep in mind what's happening here is the volume of this changes, right? As you move this rectangle left and right, it changes. In fact, if I move this rectangle all the way to the right, what's x? What's x if I'm all the way to the right? 1. What should the volume of that last one be? 0. Plug 1 in here for x. What do you get? 0. Right? That makes sense that it would be that? What about right in the middle? What's x in the middle? 0, right? So what's this length? 2. Plug 0 in here. What would you get? 2 squared, 4 times how wide it is. I hope that makes sense, but the formula is actually matching what's happening as you're moving from left to right. So to actually move left to right and add them all up is where we come in with the integral. Are we going to need a pi or a 2 pi? No, it's not part of our formula. So the volume of this solid that we're trying to find will be the integral from where to where? Negative 1 to 1 of the formula. 2 minus 2x squared squared dx. And then you could, FOIL it all out, power rule, blah, blah, blah. And I know maybe a few of you might be thinking, well, could we have just gone from 0 to 1 and doubled the answer? Could you? Yes, you're relying on symmetry for that in this particular problem. But in general, you'd have to be careful with what's happening above if it's not symmetric. All right, questions? Let's take this same problem Let's make our cross sections, what do you want, circles or semicircles or triangles? Let's do triangles first. Equilateral triangles. Or let's change this to equilateral triangles. So all of my setup is exactly the same, right? The setup's exactly the same, so I don't think I'm going to redraw everything for us, okay? I'm just going to lay that one sliver down on its side here. And now I'm going to create the equilateral triangle. Equilateral meaning all sides are the same length. Right, something like this. Very narrow slice of cheese. That's what we've got. And we need the volume of this. So what is the volume of this? Well, don't you need to know the area of this triangle, the area of this face of the triangle? And then just multiply times the width. So how about dx for width? Yes? We got that? Okay. What's the area of this triangle? I'll look at it from the side. Here's an equilateral triangle. Do you know this side right here? Do you know the base here? This side? That's that top minus bottom, right? Which we already knew was what? 2 minus 2x squared? Okay, so I know that this is 2 minus 2x squared. Okay, how do you find the area of a triangle, equilateral triangle, if you know all the sides? I know that you know that the area of a triangle is 1/2 base times height. Most people know that, right? Yes? What's the other better formula that I could use here? So this is a side note here. If somebody gives you a triangle, and if you know the height, and if you know the base, the area is 1/2 base times height. We all know that, I hope. Why is this formula not efficient for us right now? You don't know the height, right? Could you find the height? Sure, you could drop a perpendicular down, you could create a right triangle, you could do like some sort of Pythagorean and stuff like that, but we're not even going to mess with that because there's another formula that involves triangles that was from pre-cal that is much more useful here. And the formula goes like this. If you know this side, okay, A, and you know this side, B, and you know the angle between the two, then the area is 1/2 A times B times sine theta. Anybody remember that formula or remember seeing that at some point? Yeah. This is actually not a magic formula, all right? A lot of people think it's like some sort of weird, you got to know a lot to figure this formula out. Check this out. All right, I'm going to highlight that. Look at theta over here. I want you to tell me right now, from this triangle right here, if I draw a little right triangle, what is sine of theta? H over A? Wait, sine theta is H over A? Solve for H. Multiply both sides by A. What do you get? A sine theta is H. Okay, go to this formula right here and replace H with A sine theta. And what do you get? This formula right here. Okay, so all it is just a real clever little application of some right triangle stuff. But it's much more useful because in this formula, I don't need to know the height. I need to know two sides, and I need to know the angle between the two sides, but I know that, don't I? Because this is an equilateral triangle. If it's equilateral, all angles are the same, so all angles are 60 or pi over 3, right? And I know this side here was 2 minus 2x squared. So the area of that little triangle is 1/2 A times B. What's B? Same thing, so square it. What is sine of 60 degrees? √3/2. Y'all see where that all comes from? I didn't have to draw any, I didn't have to break up that triangle or anything. I just used that formula. I'll connect this here so you can see it. This, all right, comes from there. Okay, so then what is the volume of this little piece right here? What's the volume of this then? It's this right here, right, times dx. So how about we write √3/4 instead of having those constants separated? 2 minus 2x squared squared dx. That's the volume of that one little piece. Are there any questions? No? Now we set up the integral. So our integral is going to go -1 to 1 of √3/4. Yes, you could pull that out. It's a constant. That would be the setup. Questions? Then I would have to have some information about the triangle. You're saying, what if it's a triangle but not equilateral? Then someone would have to give me the relationship. You know, like, okay, the base is the 2 minus 2x squared, and then somehow relate to me the other sides. I would have to have that information. But as long as I've been looking in calculus books, they never really ask that. It's always equilateral triangle. Yeah, it's kind of the standard approach. How about a circle? Let me do a circle quickly. You got something important going on today? Okay. You want to do semicircle or full circle? Full. You want to go full circle? All right. So full circle, right? It would go like this. It would come around. So we're doing circles right here. Circles, the diameter is the base. All right. So that red rectangle that we're laying down on the ground, we're assuming that that's the diameter of our circle. So we already know the dx part, right? You just need to find the area of the face of this circle. And the area of the face of a circle, or a circle, is pi r squared. What's the radius? We know the distance all the way across, right, is what? 2 minus 2x squared, but we want half of that, right? So it'll be dx is the width, and then this front area is equal to pi times the radius, which is half of the diameter, right? Squared. And then, of course, you could distribute the 1/2 through and just make that a 1 minus x squared, and then squared. So pi 1 minus x squared, and then all that quantity squared. Any questions? So give me a final volume formula for the whole thing. Integral -1 to 1. You could pull pi out. It's fine. You could leave it in also. It doesn't matter. 1 minus x squared, quantity squared dx. That would give you your volume. And then if it was a semicircle, what would be the only difference? You just take half of that, right? So up here, you would have just said this formula right here for area, you just would have thrown another extra half on the outside. All right, that okay? You could do it with respect to y, you could, but I believe everything that is in this text is off with respect to x. It would be the same thing, you just switch your x and y. Yeah. Okay, so as far as homework, on page 380, I already gave you some problems from 379, right? So from 380, number 42, '43 is one where they tell you they're isosceles triangles with a height equal to the base. A height equal to the base. So you got to mess with that a little bit. That's a good example of what you're asking. What if the triangle's not? Let me see, 40. You know, 40 and 41 wouldn't be bad just for practice. Okay, so those problems right there are these perpendicular cross-section problems. But for the shells method, that's from 7.3, that's the next section, and that comes off of page 385. And you should look at problem, let's see, where is it? Problem 3, 6, 15, 16, and 17. So this is all shells over here. Shells, this is perp cross sections. Y'all with me? Understand? Okay, we're going to move on. We still have some time. All right, we are moving into 7.4. Arc length. So here's the idea behind arc length. We have a curve, a function. Let me draw it a little different. It may be easier for me to do this. There's a curve, okay? We're going to be looking from A to B here. We already know how to do a lot of things to this, right? We can find the area below it. We could find the area below it, rotate it around the x-axis. We could find the area below it and rotate it around the y-axis, which if I were doing, I would do shells, wouldn't you? Okay, and I mean, you could rotate around different lines, but arc length is a completely different concept. So what we're doing is we're taking this curve, and we're taking it off the page, and we're straightening it out, and we're measuring how long it is. Well, we're going to do exactly what we've been doing. We're going to have to try and come up with a formula that would represent what we desire to have, which is the length of that, right? Understand what we're doing, though? The length of the arc. So if this is some object that's traveling over some curve, we want to find out what the total distance traveled was. right? So how do we do this? Here's the approach. What we'll do is we'll get our little magnifying glass here, and let's just zoom in on this little infinitesimal piece of this arc, right? So I'm going to zoom in on it here. When I zoom in on it, I've got a little piece of arc there, don't I? And I'm going to construct from this a right triangle. This. Now, if I construct a right triangle, the hypotenuse, right? The hypotenuse is not the blue, right? But it's approximately very close to the blue, isn't it? And if I get this triangle even smaller and smaller and keep zooming in further and further and further, the error that I have in my hypotenuse versus the curve gets smaller and smaller and smaller. So this is very similar to when we were doing the Riemann sums, and we knew that the more rectangles we had, the less error we had. Same thing here. I know the further I zoom in, the less error I will have. And so I'll eventually want to zoom in infinitely many times, right? And make these infinitesimally small. But for now, let's just take a look at this. Right here, this side of this triangle we could call our change in x. We start at some x coordinate, we change it by this much, and then we wind up here, right? On the curve. So this will be called change in y. Our approximation, this length, that line that I just put there is approximately the length of the blue one. What's the length of that red line that I just put in here? This will be a squared plus b squared is c squared, right? So c would be the square root of delta x squared plus delta y squared. Do you all follow that? That would be the length of that one little piece. Now what I need to do is get this in terms of like dx or dy, because this was just an arbitrary rectangle. What I want to do is go to the infinitesimal now, make this delta x change to a what? If we go to the infinitesimal, that means we let the number of these go to infinity. Dx, and this one will change to dy. Yes? Okay, now I want to remind you before we move on, I want you to recall something. Recall, back from Calculus 1, that whenever we wrote y prime, what we meant was dy dx, right? These were the same two things, just different notations. Yes? So if I multiply both sides by the differential dx, I get y prime dx equals dy. Agreed? Okay, keep that in mind. Because now what I'd like to do is take this, and go to the infinitesimal. If I go to the infinitesimal, this changes to square root of, instead of delta x, what? Dx squared plus, instead of delta y, dy squared. Yes? Y'all still with me? See, here's the thing. I should probably have pointed this out. I mean, at this point, you might be saying to yourself, well, let's go, just add these up. We have a formula, right? We have a formula for the length of that. So why not just add them up? In all of the formulas we've always had before, haven't we always had at the very end of it dx or dy? We do not have a dx dy. So you would have an integral without a dx dy in it, which you have to have because that shows you what you're integrating with respect to. So I'm not there yet where I have that dx or dy popped on the outside. So I need to go to a new page. What did we say dy was just a second ago? Y prime dx. So that's the same? Is what we just got? But that's the same as this. And since these both have dx squareds in them, I can factor out a dx squared. Which would leave me with what here? 1 plus y prime squared. And since I have multiplication here, I can split this into 2 square roots. And what's the square root of dx squared? Dx. And there's that dx that I wanted to pop out, didn't I? I wanted that to happen so I'd know what I'm integrating with respect to. I'll put it on the outside here, on the back side of this. That is my formula that I can use in my integral. That's that approximate length. Add them all up, integrate it. Any questions on where this comes from? No?
Where do you get the 1 plus the y prime?
Right here, these are common factors. This and this appear in both, so I pull out a dx squared from this and this. When I pull it out from here, I'm left with the 1. Pull it out from here, I'm left with the y prime squared. So, in conclusion, the length of that the length of the entire curve, okay, the length, capital L, should be equal to the integral, adding them all up, from a to b of that formula we just came up with, the square root of 1 plus y prime squared dx. If I can integrate that, I'm in business. If I can integrate that, I'm in business. The fact that this integral contains a square root, the formula for arc length contains a square root, creates a lot of issues because that integral can be tough. Yes? Mm-hmm. What do you mean? Like, if it would have come down this way? I'm not sure I understand. You're saying if this was a function of x instead of y, you could set it all up the same way, except what would change here would, where is it? This would be, what do you think, x prime, and this would be dy. Yep. So it would be the same thing, variables switched out. And then c and d instead of a and b. What's that? I'm not going to give you any arc lengths of curves that are functions of y. I'm going to stick with functions of x. Okay, so let's do an example. And let me show you that these can become nasty, all right? And then you'll appreciate the problems that I'm going to give you afterward. All right, let's try and see if we can use this to find the circumference of a circle, radius capital R. What is the circumference of a circle? We all know it's 2 pi r, right? Okay, let's see if we can come up with that formula on our own. So let's start with this. Here's our circle. Do you remember we did this earlier, but we did this for the volume of a sphere. So we took a quarter of a circle, and we rotated around the x-axis, and then we doubled that answer. We got 4/3 pi r cubed. This time, I'm going to take an arbitrary circle, radius capital R. I'm going to try to verify that the formula is 2 pi capital R for the circumference. So, but I'm going to act like we don't know the formula, so I'm going to maybe do arc length. I'm going to find the length of this arc right here. How about we just focus on that one piece? And then we'll multiply that answer by times 4. Y'all okay with that? we first need to write this one little piece as a function of x. So do you remember how we did that? X squared plus y squared was capital R squared, and we solved for y. And we got y was equal to the square root of capital R squared minus x squared. This is all in your notes, right? From before. So if I want to find the length of this arc, what's my formula going to be? Length is integral where to where? A to B. What's A for us here? 0. What's B for us? Capital R square root of 1 plus what? The derivative squared, right? The derivative of y squared. That means you have to go find the derivative of y, which means on the side here, scratch work, I need to take y, and I need to find its derivative. So what's y prime? Well, this is chain rule, right? The derivative of the square root of something is 1 over 2 times the square root of that something. So 1 over 2 times the square root of that something times the derivative of what's inside with respect to x. So what's derivative of capital R squared? 0. What's the derivative of negative x squared? Negative 2x. And so the 2's cancel here. So what we get is that y prime is equal to negative x over square root of capital R squared minus x squared. Y'all okay with that? Now, go back and look at the formula we just had. We don't want to plug y prime in there. What do we want to plug in? Y prime squared. Y prime squared goes in there. So let's write down underneath this, what's y prime squared, just so we have it. X squared over, squaring the square root. I'm happy. I'm a happy man, right? And then that piece right, that's a squared up there. That doesn't look like a squared. Okay, this is the derivative squared. So squared the top and the bottom. That piece goes right there next to the 1. So my length is equal to integral 0 to capital R square root of 1 plus x squared over capital R squared minus x squared, all of that dx. Ooh. So how would you integrate this? Well, we have 2 terms underneath the root, right? Yeah. How about we try and get the 1 plus that fraction, put them together, get a common denominator? Let's try and squeeze these 2 together. So if I did that, I have to put what over here? R squared minus x squared over r squared minus x squared. When I have r squared minus x squared on top and I add it to x squared, what's the only thing left? R squared. So this is going to be integral 0 to capital R square root of, you said it was just r squared on top over the common denominator? Dx? If I have a fraction under a root, I can split it into 2, right? And so the top would be the square root of r squared, which would be what? Capital R. Can I pull that out of the integral? Yes, because r is a constant. So I can pull a capital R out of the integral, then integral from 0 to r. What's still in here? 1 over square root of r squared minus x squared dx. And that looks like a squared minus u squared. That's a formula. But if you forgot the formula, what could you use? Trig sub. Trig sub. right? You'd use trig substitution. But let's go to the formula. Someone tell me what formula that is, what number? I'm hearing 16 and 17. Which one is it? Which one? 16? Oh, and sorry, I don't want the integral anymore. What is the antiderivative of this according to formula 16? Remember, A is R, capital R, right? So what is it? Arc sine of x over R. Everybody agree with that on formula 16? And we put our limits of integration from 0 to capital R. So we first start by replacing x with R. So let's plug R in here. What's R over R? So I have my two things here. R over R is 1. What's the arc sine of 1? So sine of what angle gives you 1? Pi over 2. I'll write it down. Capital R of arc sine of 1. And then when you plug in 0, you get capital R arc sine of 0. So this is capital R times, you said the arc sine of 1 was pi over 2, because sine of pi over 2 is 1. And then minus, what's arc sine of 0? 0. Remember your domain restriction, you're between negative pi over 2 and pi over 2, so you can only be over at 0. So this is 0. So your answer is 1/2 pi capital R. I wrote it that way because that was only one of 4 segments, right? So multiply this answer times 4, and what do you get? 2 pi R. So we just verified the circumference formula is correct. Yeah. Good thing, huh? Okay, so we're at a point where we're going to have to stop because we don't have enough time to do another example. But let me just tell you, the trouble we're going to run into is that when you take the derivative over there to plug into the formula, when you take the derivative to plug in right here, right? That derivative squared has to be chosen in a way, like the original function has to be chosen in a way that when you put it together with this 1, you can integrate that. And in general, it's very difficult to integrate these, which is why when you do your homework, you'll see that the functions they give you look weird. It's like all of a sudden, it's like, wow, why are they giving me these strange looking functions? The reason why is because they want to make sure that the derivative squared plus 1 is something you'll be able to do. And so we'll see next class a couple of more examples of this. And then we'll finish up surface area. So what are we doing next class? This is our last class before the test, right? Yeah, so we have next class, we'll do a couple more of these. Let's do surface area, and we'll talk about the test. Applications of integration to physics, let's move that to the next test, because I don't think I can squeeze 7-6 in next class. All right? Sound fair? All right. Arc length and surface area will be on the test. Yep. We haven't done surface area. That's what we'll do next class. Are you talking about what's going to be on the test?